We're gonna start with number 7. Okay, this is the one we left off with. So we did 1 through 6 last time. So we're gonna go through 7, 8, 9 today. So again, drawing pictures here. Okay, so we're gonna see a balloon leaves the ground 500 feet away from an observer and rises vertically at the rate of 140 feet per minute. So let's draw this. So there's an observer that's watching a balloon. Okay, so let's see, the observer probably 500 feet away from an observer and rises vertically at a rate of, so okay, let's put a balloon here. They say, so this would be my y value, right? If I wanted to list it, this would be my y value, okay? So I'm going to have to find the rate of change, they tell me, my dy dt. They tell me that that's 140 feet per minute. So dy dt equals to by 140 feet per minute. So there you go. So a balloon leaves the ground 500 feet away from an observer and rises vertically at the rate of 140 feet per minute. So far I have everything that they've mentioned in that first sentence. Now it says, at what rate is the angle of inclination of the observer's line of sight increasing at the instant when the balloon is 500 feet above the ground? So to kind of connect this stuff, I know it's not at the person's eye. That's where it's supposed to be, but it's okay. You can do it from the ground. It doesn't matter. So they're basically saying, at what rate is the angle of inclination changing? So d theta dt when the balloon is 500 feet above the ground. So y equals 500. So this is the main question for us, okay? Now, if you notice what they've given us a theta value, right? That's what we're having to figure out. A y value and a 500. Now, we know the 500 is not going to change, okay? They didn't mention anything about that changing. So let's use a tangent, right? Let's try using tangent here because that deals with opposite over adjacent. So tangent theta is equal to y over 500. Okay, remember I can put the 500 there because it's not changing. They didn't say anything about the balloon getting closer or further away. There was no mention of wind or anything like that. So it's just going straight up. Okay, so once we have that, we're going to take a derivative of both sides. So the derivative of tangent of theta is secant squared theta d theta dt. Now the d theta dt, that's exactly what we need to solve for. The derivative of y over 500, that's the same as 1 over 500 times y. So the 1 over 500 is just a constant. Ignore it. But the derivative of y is just dy dt. So this is 1 over 500 dy dt. Now we got to solve for d theta dt. So d theta dt is equal to 1 over 500 secant squared theta dy dt. Okay, and then I'm going to change the secant squared theta into cosine squared theta. So we kind of did this in another problem with the kite, if you guys remember. It was very similar. So dy dt. So this is what I have right now as my main function to try to figure out the rate of change of the angle of inclination. So they did mention to figure out d theta dt when y equals 500, right? So d theta dt when y equals 500 is equal to something over 500, and then dy dt, the rate of change that the balloon is moving is 140. Okay, now I just got to figure out what cosine of theta is. So I'm going to go over here. This is 500, and this is 500. Okay, so we just have to figure out our values to find cosine. So cosine, I need the adjacent, and I need my hypotenuse. Well, the hypotenuse is going to be 500 squared plus 500 squared equals to, let's call this our r value, so r squared. Okay. From there, just kind of combine, combine everything together. So we have the square root of 500 squared plus 500 squared equals to r. I'm sorry, just equal to r. That's plus or minus. Okay. What do we get for 500 squared? That's 25. 1, 2, 3, 4. Plus 25, 1, 2, 3, 4. That's that. I'm just doing this in my head here. So that's 500,000. So that would be 500 radical 2 equals to r. Okay, so that's my r value. So if I just cancel that out right here, I get that this is equal to 140 radical 2. That's the rate of change of the angle of inclination. So I'm going to put radians per minute. All right, and then of course you got to write a sentence about it, right? So the angle of inclination is changing at a rate of 140 radical 2 radians per minute. Actually, wait a minute. Is
because of the iPod. Yeah, it's supposed to put the
I was supposed to square it, but hold on. I just saw something that I did not. Is that square root correct?
Should be.
Yeah. Is that 500 rad 2?
Yeah, it is.
Yeah, it is. Yeah, 25 times 2 is 50. Okay, so that's good. I did just realize right now I forgot to square it, right? So give me a second. Hopefully I can fix it and not erase the boxes. Let's see. Yeah, I just realized right now, I'm like, that doesn't seem right. But let's see if maybe we can just do that real quick. So it's supposed to be 500 radical 2. Hold on. Cosine theta would be 500 over times 140. Okay, so maybe I'll count on you guys to do this next part for me here. But this will be 500 over 500 squared times 2 times 140. That'll cancel out. One of those 500s on top, the 500 squared on top, I'm canceling out with the denominator. Okay, so there's supposed to be 2 here, but I'm going to get rid of it to get rid of that one. So that's how I did what I did. But now I'm going to kind of count on you guys here. Let's see. Let's do some scratch work on the side. So this is going to be 1 over 1,000. That'll be 140. That's 14 over 100. 7 over 50. Yeah, that should be it. Double check me, but I think that's right. Yeah, when I saw the answer, I'm like, that's moving really fast. So that would be better. So yeah, let's fix that. At first, I was looking at my square root, and I'm like, is that correct? So I was kind of double checking that, and then when I looked where I plugged it in, I'm like, wait a minute, I didn't put it into my cosine. I just put it as my R value. So that was incorrect. So we had to fix that really quick. So before I move on, any questions on either the correction or the thought process going into that? Are we good? So pretty much like the kite problem, okay, that we just did. I think it was example 4. All right, so let's look at 8, and you'll notice 8 and 9 are both ladder problems. Okay, so number 8 says a ladder 13 feet long is leaning against the side of a building. So I don't know, we'll just say the building is here. So there's your windows in the building, etc. So the building goes up. Okay, so there's a ladder leaning up against the building. We'll make sure it's a decent sized ladder. Okay, so a ladder 13 feet long. Now, is the ladder going to change size? No, they just say it's 13 feet. So that's a constant, okay? So 13 feet long is leaning against the side of a building. If the foot of the ladder is pulled away from the building at a constant rate of 2 inches per second. So notice this would be my X and this would be my Y. So they're saying if we were to pull the ladder this way, the foot of the ladder gets pulled away from the building at a rate of 2 inches per second. So dx dt, my X value is changing. Dx dt is 2 inches per second. How fast is the angle formed by the ladder and the ground changing? So ladder and the ground, this would be right there. Okay, so ladder and the ground, that's right on the bottom right portion of that ladder. So they want to know how fast is the angle that the ladder and the ground make when the top of the ladder is 12 feet above the ground. So when y equals 12 feet. So what equation should I use? I mean, what shape are we dealing with? Triangle. You notice we got an xy and a hypotenuse, right? So which equation? Pythagorean. Yeah, we're going to use Pythagorean. So x squared plus y squared equals 13 squared. Remember, I am plugging in a 13 right now because it is a constant ladder. They didn't say that it changes. It's not like one of those little giant ladders that they sell now that it can be 5 feet, 12 feet, 18 feet, right? It's 13 feet, they said. So we're going to take a derivative. So that's 2x dx dt plus 2y dy dt is equal to 0. Now get rid of all the 2's because we're just going to divide everything by 2. And our objective here is to find what? D theta, right? Am I going to be able to do that with this? No. Right? I can't do it with this. Why not? There's no theta, right? We need something with theta in it. What I'm kind of showing you guys right now is a lot of times when we do these problems, we look at pictures and we say, I can see Pythagorean theorem, so let's do that, right? But yeah, again, you want to look at your goal, and our goal is to find an angle, right? So what angle should I use? Well, I mean, if I were to use well, I don't want to use tangent, right? Because it'd be tangent theta equals y over x. And that's three variables. I don't know, Mo. I could use cosine or sine, but which one would be better? Why cosine? Because I have an x in the cosine, and then when I take a derivative, I'll have a dx dt, right? So it would make more sense for me to use something that includes an x value so that I could have a dx dt pop up. So this stuff right here, this is how you know that something's off, because when you do your derivative and you're like, wait a minute, I'm supposed to solve for d theta dt, how am I going to do that? You can't, right? So we're going to do cosine of theta is equal to x over 13. Okay, take a derivative. So I get the derivative of cosine is negative sine theta d theta dt equals to, that's a 1/13 x, so the 1/13 is going to stay. The x becomes a 1, so it'll be dx dt. Okay, so I'm going to get d theta dt by itself. That becomes a negative 1 over 13 sine of theta dx dt. Or if you kind of want to rewrite it so it doesn't have so much stuff in the denominator, you can bring that sign up and make it a cosecant like that. Now, I know what dx dt is. That's a 2. But I don't know what cosecant of theta is yet. But they did tell me some information about it, right? They said when y equals 12. So let me draw, actually I'm drawing the wrong picture here. We know that the latter is 13. We know that this is a 12. So that means that the other side should be a what? This should be memorized. This is a Pythagorean triple. There's a 3, 4, 5 triangle and then a blank 12, 13. That's a 5, yeah. Then after that it's 7, 24, 25. That's the next triple. Okay, you guys should know those. Okay, I'll put them right here. A 3, 4, 5. There's a 5, 12, 13, 7, 24, 25. After that, it's okay if you don't know them. Did I? Oh, I put in the wrong place. Sorry. Yeah, thank you. 12 doesn't change the answer in a sense of the numbers, but yeah, it will change the order in which they see them. So, but yeah, the Pythagorean triples 3, 4, 5, 5, 12, 13, 7, 24, 25. Make sure you guys know those because they pop up a lot. So all I need to figure out is cosecant, right? Cosecant would be hypotenuse over opposite. So 13 over 12. Cosecant theta will be 13 over 12. So let's plug that in. So negative 13 over 12 divided by 13 times 2. Well, these 13s will cancel out. Okay, so all I have left is a negative 2 over 12, which is just a negative 1/6. Now that's an angle, so it's radians per, what are my units? Seconds, right? So radians per second. So there's my answer. Now, does it make sense that the answer is negative, or should I be worried? Yeah, if the ladder is going down, if it's falling, that angle is closing, right? So it makes sense that the angle is getting smaller. So you could just put the angle is getting smaller at the rate of 1/6 of a radian per second when y is equal to 12.
Mr. Reed,
Uh-huh.
the dx dt, that was 2 inches. Shouldn't it be converted to feet?
Did I do everything in terms of feet? Hold on. Let me erase this really quick. I'll make the mark and then
Yeah.
give me a second. All right, radians, inches. Oh yeah, and we did feet. So what would dxdt be in feet then?
1/6.
Yeah, let me fix that really quick. Thank you for that. So that would be a 1/6. I'm going to put right here as 2 inches is equal to 1/6 of a foot. Okay, so let me fix that here. So this would be still negative. 1/72. 1/72 radians per minute. Notice I didn't put negative on the answer because I said it's getting smaller. If you don't want to say that it's getting smaller, just say that the angle is changing at a rate of negative 1/72 radians per second. But it's up to you how you want to state it. I usually give direction whenever I'm writing the answer. So it's moving left, it's moving right, up, down, shrinking, growing. That's the way I tell them about the plus or minus. But you don't have to do that. You could literally just say the rate of change of the angle is this when the following is true. All right, so the next problem is kind of the same, okay? Not identical, but kind of the same. So number 9, last one here. So it says a ladder 13 feet long is leaning against the side of a building. If the foot of the ladder is pulled away from the building at a constant rate of 8 inches per second, how fast is the area of the triangle formed by the ladder, the building, and the ground changed in feet squared per second at the instant when the top of the ladder is 12 feet above the ground? So almost the same setup, right? We have a building, we have a ladder. So, and then we know that's 13 feet. But they want to know the change in area. Here's x, here's y, and they tell us that dx dt, the rate of change that the ladder is being pulled away, is 8 inches per second, which will become 8/12 feet per second, right? So if you reduce that, that becomes 2/3. Yeah, 2/3. 2/3 feet per second. All right. So a ladder 13 feet long is leaning against the side of a building. If the foot of the ladder is pulled away from the building at a constant rate of 8 inches per second, so we wrote that down, how fast is the area of the triangle formed by the ladder, the building, and the ground changing? So they want to know the rate of change of the area. Okay. When the top of the ladder is 12 feet away. So obviously in this case, we're going to have to figure out the formula for the area, which is not that hard to do, right? Area is equal to 1/2 x times y. Okay, base times height. What is our issue with this problem? We have too many, we have too many derivatives, right? We have too many derivatives, or too many variables, sorry. So what can we do with this problem when we're going through? Like, what are we going to try to find? I mean, we don't know dx, we know dx dt, but we don't know dy dt, right? Is there a way that I can find dy dt? Yeah, let's try the Pythagorean theorem, right? If I do the Pythagorean theorem, let's do that over here on the right side. X squared plus y squared equals 13 squared. I get 2x dx dt plus 2y dy dt equals 0. If I cancel out those 2's by dividing everything out, I'll get x dx dt plus y dy dt equals 0. So it'd be really nice if maybe, let's see, I have a dx dt that they give me. Why don't I get rid of my y's, right? Let me get rid of the y's, replace them with a bunch of x stuff, and that way I can have variables that I know how to use. Okay, so in this case I have, let's see, I'll move the dy dt equal to negative x over y dx dt. Okay, so I know I still have a y there, but that's okay because I'm supposed to have one y. How do I know I'm supposed to have at least a y variable? Yeah, they say y has to equal 12, right? That means I got to plug it in at some point, okay? But the one thing I don't know is my dy dt, but look, I just solved for it. Now I know what dy dt is. So when I do this area, I'm going to have a dx dt, I'm going to have a dy dt, but I know what dx dt is, and now I know what dy dt is. It's negative x over y dx dt. Okay, so we're good. Right now we have 3 variables, usually not a good thing, but we were able to figure some stuff out. Okay, so dA dt, is equal to half. The derivative of x is 1, so it's y dx dt, plus then x and the derivative of y is dy dt. So notice, the y that I need to plug in over here is going to become a 12. So that's fine. That's good. Dx dt, I know it. That's good. X, I don't know it yet, but I could figure it out because if y is 12, then x has to be 5. So that's good. And dy dt, well, that's over here. But I know what x is going to be. That's going to be a 5. The y is going to be a 12. The dx dt is going to be a 2/3. So I know everything. I just got to plug everything in. It's going to look really messy at first, but let's see. We have dA dt when y is 12 equals 1/2. Now, y is going to be 12. Dx dt is 2/3. Okay, because we're doing it in feet per second. Plus x. Well, we already talked about this before. With the triangle, I drew it backwards again. With our triangle, we have a 13. They're saying this is 12, so this has to be a 5. So this is going to be 5. Now, dy dt. Dy dt is negative x over y. That's 5 over 12. Dx dt, that's 2/3. So the stuff in green comes from dy dt, okay? That's this stuff right here comes from here. All right, when you guys do all that work on the right side. So now I guess the hard part is to try to break everything down nicely. So just be careful here. This is usually where I'll make mistakes. You know, it just happens because you're trying to break everything down little by little. So 12 times 2 over 3, or 12 divided by 3 is 4 times 2. That's 8 minus, we have 25 over 18 because the 2 and the 12 will reduce to 1/6. 3 times 6 is 18. The 2 will go away. We got 5 times 5, so there's that. Take the half in. That's 4 minus 25 over 36. Okay. So if we subtract 4 minus 25 over 36, what do we get? That's 3 and... because that's not a whole, so that's a 9? No. 11/36. What is the calculator?
It's 119 over 36 squared.
But what is that in improper?
Oh,
36 times 3, that's an 8, 108 plus 11. Yeah, 119 over 36. So there you go. Feet per second. All right. Feet squared. I'm sorry, feet squared. Just remember this was area. Okay, so just write a sentence and you're done. So the rate of change of the area is 3 and 11/36 square feet per second when the height is 12 feet.